So, dear colleagues, after several trials, we managed, and I am glad to introduce our today's speaker, Eugene Ferapontov from Loughborough University. You will see the title. Eugene, you are welcome. So it's time to begin, I think.
All right, thank you very much.
Just a moment, please switch off your microphones. Except for Zhenya.
Yeah, you can hear me well, right?
Yeah, it's perfect, Zhenya.
Okay, fine. And can you see my cursor? Annotate.
Yes, we see the screen and you see your cursor and you see you. Okay.
No. You see my cursor, yeah?
We do.
Okay, now maybe. Just a second. No, this is not what I want. All right, thank you very much. So I will speak about our joint recent work with Sobi Berzhavi, Borya Kruglikov, and Volodya Novikov. Okay, let me go to the next. Oh, dear. Next slide. So this is the plan. Maybe I will summarize first in 2 words what the talk is about, and then I'll go through everything in detail. So we are looking at arbitrary second-order PDEs in 3 dimensions, scalar PDEs. Just a one single second-order PDE for a function of 3 variables. And we allow this PDE to depend on all variables, second-order, first-order derivatives, the function itself, and independent variables. And okay, every such PDE has a symbol, principal symbol, and this principal symbol defines a conformal structure. I will explain all this in detail later. So principal symbol defines a conformal structure which depends on the solution. So every solution of every second-order PDE has a conformal structure. And then we require this conformal structure to satisfy certain integrability property on every solution. Namely, I will require that this conformal structure is Einstein-Weyl on every solution, right? And the question is, what can we say about such PDEs? Can we classify them? So maybe in some classes, what are their properties? So this is what the talk is about. There are some conjectures, there are some partial results. So this is what I want to discuss. So I will start by explaining what Einstein-Weyl geometry is. There will be just one geometric slide. Then I will show that Einstein-Weyl structures can be parameterized by a familiar PDE system, which is known as the Manakov-Santini system, right? And then I will discuss what we can say about PDEs for which this conformal structure is Einstein-Weyl, characteristic conformal structure is Einstein-Weyl on every solution. I will first discuss Hirota type equations in 3 dimensions, and then the main subject of my talk, general third-order PDEs in 3 dimensions, second-order PDEs whose conformal structure is Einstein-Weyl on every solution. And I will discuss 4 aspects of these PDEs, namely that such structure, this requirement of Einstein-Weyl, the Einstein-Weyl property, can be viewed as a dispersionless integrability test. So it can be effectively verified by computer, of course. Then I will show you partial classification results of PDEs which have Einstein-Weyl conformal structure in every solution. Then I will show that this directly leads to dispersionless Lux pairs by a certain explicit formula. If you know your equation is Einstein-Weyl, then you can write Lux pair explicitly. And then I will formulate a rigidity conjecture, which essentially says that in generic second order PDEs with Einstein-Weyl conformal structure, all dependence on low order jet variables, namely first order jet variables, can be eliminated by a contact transformation. So it is unessential in some sense, but this is a conjecture. So it's based, the talk is based on our recent paper. All right, so go to the next slide. This is Einstein-Weyl geometry. So this is the only geometric slide without equations. So what Einstein-Weyl geometry, in principle, it exists in any dimension, but it is particularly interesting in dimension 3. So I will assume that we are in 3D. We are on a 3 manifold, all right? Einstein-Weyl structure is a triple. It consists of D, which is a symmetric connection. Then G is a metric, Riemannian Lorentzian metric. In fact, we will see later that it is conformal structure makes sense, not the metric itself. A metric considered up to a factor, but we can think of this as just a metric. And then a k-vector, a one form omega. So we have a triple: symmetric connection, metric, and one form. And they satisfy these two sets of equations. These are called Weyl's equations. They say that if you covariantly differentiate the metric with respect to this connection D, the result will be proportional to the metric. Imagine that in this equation, omega is 0, right? Then you have dkgij is 0, and D is a symmetric connection. This is the definition of a Levi-Civita connection of the metric, and we know it's unique, right? There is a unique symmetric connection in which the metric is covariantly constant, all right? But now assume that omega are given to you, and they are, so these are given functions. Then these equations still define you a connection uniquely. Once you know omega and G, you can reconstruct this connection D uniquely from the first set of equations. So in fact, in this triple, G and omega are important things, and D can be reconstructed. It's secondary, right? And the second set of equations are Einstein equations, Einstein's equations, which say that the Ricci tensor of this connection D is proportional to the metric. And here round brackets denote symmetrization, because Ricci tensor of a non-metric connection doesn't need to be symmetric, so you have to symmetrize it. And lambda is some function, coefficient of proportionality. So we have Weyl's equations and Einstein equations, so it's called Einstein-Weyl geometry. Remarkably, it was introduced not in general relativity, but in the context of third order ordinary differential equations by Lee Cartan in 1941, right? Before I proceed to Cartan's theorem, let me say a few words about conformal invariance. It turns out that if in these equations, in this set of equations, you change G to lambda G, where lambda is some function, you scale G, then you add to omega the logarithmic derivative of lambda, and D you keep the same. The connection stays the same. Then these equations will still be satisfied, right? So it's a sort of gauge symmetry of these equations, which essentially say that we are dealing with conformal geometry, because G is defined up to a conformal factor lambda, right? So it's conformal geometry. And then Cartan proved the following theorem. I will state it, and then I will explain what the terms in this theorem mean. So in the 3 dimensions, this triple dg omega satisfies Einstein-Weyl equations, these equations, highlighted equations, if and only if in this 3-dimensional manifold there exists a 2-parameter family of surfaces which are simultaneously totally geodesic with respect to the connection. I will explain what this means. And there must be null with respect to the metric, right? What means that a surface is totally geodesic in a connection. Let me first explain this. Okay, let me take the simplest picture, three-dimensional Euclidean space, right? It has flat connection. Its Christoffel symbols gamma are 0 in flat coordinates. So take a sphere, take a round sphere, and take a tangent vector to the sphere. Then through a point on the sphere in this tangent direction, there is a geodesic in free space passing through this point in this direction. And this is clearly a straight line. Geodesics in Euclidean space are straight lines. Clearly, this geodesic, it starts on the sphere in the tangential direction to the sphere, but it escapes from the sphere. This means the sphere is not totally geodesic. Which surfaces are totally geodesic in Euclidean free space? These are only planes, two-dimensional planes. If you take a two-dimensional plane, a point on this plane, and the tangential direction, then the line in this direction through this point, it will stay on the plane. So plane is totally geodesic. And this concept of totally geodesic surface makes sense in any space supplied with connection. So we say that a surface is totally geodesic if, when you pick a point on this surface and the tangential direction to this surface, then a geodesic in free space through this point in this direction remains on the surface forever, right? Such surfaces are called totally geodesic. So they consist of a two-parametric family of geodesics, right? Swept out by geodesics, by a two-parametric family. Now, so I explained what totally geodesic means. Now, what means that a surface is null with respect to the metric? Right, this is simple. You just restrict the metric to your surface. If what you get is degenerate, determinant of the restriction is 0, right? Then the surface is called null with respect to the metric. A restriction of the metric is degenerate. Alternatively, another way to express this is the following. Take null cones of the metric. We assume Lorentzian signature. So the metric has null cones. At every point, you have a null cone. So a surface is null. If it is tangential at all points, it is tangential to null cones. So all null cones are tangential to the surface, right? So, and Cartan proved that these conditions are equivalent to the existence of two-parametric family of surfaces which are totally geodesic in this connection D and null with respect to the metric G, right? We will see on the next slide that this property is equivalent to the Lux pair. In fact, it's a geometric reformulation of the concept of a Lux pair. And we will see it explicitly on the next slide using formulas, right? Then Cartan proved in the same paper, I guess, that Einstein-Weyl structures, namely solutions of this highlighted system, locally modulo changes of variables, depend on 4 arbitrary functions of 2 variables, 4 essential functions of 2 variables. It's not clear from these Einstein-Weyl equations, if you look at them, right? But it will be clear from the representation I will show you on the next slide. So we have a freedom of 4 arbitrary functions of 2 variables. And finally, it was proved by Hitchin that 3D Einstein-Weyl equations are integrable by the so-called twistor construction. Again, integrability will be seen on the next slide. Okay, now I move to the next slide. And this is, Einstein-Weyl structures via the Manakov-Santini system. So this Manakov-Santini system, you can see it here, right? You can see it here. It's a system of 2 PDEs for 2 functions. We have 2 functions, u of x yt and v of x yt. And we have this PDE system. You see, if we set v equals to 0 in this system, v equals to 0, then this equation just disappears. Everything is 0. Then these 2 terms disappear because they involve v. And we are left with the dispersionless Kp equation. Namely, this bit equals 0. It's dispersionless Kp equation. So this Manakov-Santini system can be viewed as a 2-component generalization of dKp, right? And then Maciej Dunajski, somewhat later, he observed that if you have a solution u of x, yt and v of x, yt to this system, and you introduce the metric by this formula, metric G, and you introduce covector omega by this formula, then, okay, we know that if we know G and omega, we can reconstruct the connection, and then this pair satisfies Einstein-Weyl equations, right? So Einstein-Weyl equations for this pair is equivalent to the fact that U and V solve Manakov-Santini system, right? So in other words, every solution of the Manakov-Santini system gives you Einstein-Weyl structure determined by G and omega shown here, all right? Then later we proved in a joint paper with Maciej and Boris that all Einstein-Weyl structures arise in this way. So the Manakov-Santini system parameterizes all Einstein-Weyl structures, right? So what can we see from this? What can we deduce? So if we have a second order PDE in 3 dimensions, what is the freedom in the general solution? Clearly, you can suppose you are solving Cauchy problem, then you can determine, think of a wave equation in 3 dimensions. Then you have initial position and initial velocity. These are your Cauchy data. These are 2 functions of 2 variables, right? So one PDE in 3 dimensions has a freedom in 2 functions of 2 variables. Now you have 2 coupled PDEs. The freedom is clearly 4 functions of 2 variables, right? So the general solution of the Manakov-Santini system locally is like 4 functions of 2 variables. And this is the freedom in Einstein-Weyl structures, which I stated on the previous slide, 4 functions of 2 variables. They can be seen clearly from this representation, right? This system possesses a Lux pair. Who found this Lux pair? Maybe Maciej, I'm not sure. Maybe Maciej Dunajski found the Lux pair. Sorry, no, of course not. Manakov and Santini found the Lux pair, because in fact, they started with a Lux pair. They wanted to generalize DKP Lux pair. So they found these 2 vector fields, Manakov and Santini, and they proved that the commutativity of these vector fields is equivalent to the Manakov-Santini system, right? These vector fields commute if and only if the Manakov-Santini system is satisfied. You see this Lux pair, it depends on the auxiliary parameter lambda, right? Lambda appears as a coefficient here, for instance, here it appears as lambda squared, right? And also we have d by d lambda, we have differentiation by lambda, right? So these vector fields live in the extended space of x, y, t lambda coordinates. They live in this 4-dimensional space. Okay, now they commute. So they form an integrable distribution in this 4-dimensional space. Okay, let me take integral surfaces of these vector fields. So we have 2 parametric family of 2-dimensional surfaces in this 4-dimensional space of coordinates x, y, t lambda. Integral surfaces of these vector fields x and y, right? So, okay, we have 2 parametric family of surfaces in this 4-dimensional space. Let's project them down. Let's forget about coordinate lambda. Project them down to the xyt space. Then in the xyt space, we get a 2 parametric family of surfaces, right? And you can directly verify, it's a simple calculation, that they are null and totally geodesic. With respect to this metric, they are null, and with respect to the corresponding connection D, they are totally geodesic. So in fact, Cartan's null totally geodesic surfaces come from this Lux pair, right? And it's a geometric reformulation of the Lux pair, right? Okay, there was no concept of Lux pair at that time, but Cartan formulated it geometrically. Okay, and integrability by twistor theory, Hitchin's integrability by twistor theory, it's essentially this Lux pair, right? So in fact, this slide explains in very familiar terms all what was said geometrically before. Right. Let me now move on to Hirota type equations. Hirota type equations. First, on this slide, I will show that every Hirota type equations has a certain conformal structure naturally associated with it. So first of all, okay, what is a Hirota type equation? Let's take a function of 3 variables. And Hirota type equation is an arbitrary PDE of this form, where f depends only on second order derivatives of this function. All right. No first order derivatives, no function itself, no independent variables x at the moment. They will appear later. So just a function depending on second order partial derivatives. Now, this equation has a principal symbol. And the easiest way to introduce it is just by this formula. This is the principal symbol. df by duij, pi, pj. Pi and pj are components of a covector, characteristic covector. So this is the principal symbol, all right? So you differentiate f by uij and multiply by pi, pj, and you take summation over repeated indices is assumed. So you sum over ij. So this is the principal symbol, and we call this coefficient, df by duij, we call it gij, right? This will be our metric with upper indices, right? So this is a conformal, this is called characteristic conformal, this is a principal symbol, and if we now invert this thing, this is viewed as a metric with upper indices. Now you invert it, take the inverse of this symmetric matrix, and you associate with it the following object. This is called a characteristic conformal structure. Xi, xj are these independent variables, x1, x2, x3, right? So I repeat, you differentiate the function f by uij. This you call gij with upper indices. You invert this, you get the matrix gij with low indices, which is just the inverse of these, right? And you contract it with dxi, dxj. This is characteristic conformal structure. It's very straightforward to compute. Let me show you an example. Okay, here is the DKP equation written in potential form, written in Hirota form. Right? So you see this equation involves second order partial derivatives of u only. Now instead of x1, x2, x3, I use xyt. Right? Just 3 independent variables. This is the DKP equation in Hirota form. This is its principal symbol. Px, py, pt are covector components corresponding to xyt directions. Right? This is, you see, df by duxt is 1. So 1 times px, pt. Df by duxx is minus uxx. So it's minus uxx px squared, and df by duyy is 1, minus 1. So you get minus py squared. This is the principal symbol. It's exactly this expression, right? This expression, right? It's this one. And now you take the corresponding symmetric form of this. This is a quadratic form. So you take its matrix, 3 by 3 symmetric matrix, you invert it, and you get, I think I wrote this formula at Iosif's seminar many years ago, right? And I did this explicitly, right? And you get this metric, right? So you take the corresponding matrix, you invert it, contract it with the independent variables, and you get this metric, right? This is the characteristic conformal structure of DKP, right? What is the property of this conformal structure? You see, this bit, it doesn't depend on the solution. But here we have uxx. So you see this metric, it depends on the solution. It depends on u, right? And okay, what can we expect from this metric? since this PDE, this DKP equation is integrable, we know it's dispersionless integrable system. So the corresponding characteristic conformal structure, it must be integrable in some sense. It must define integrable conformal geometry on every solution. And it turns out that we know an example of integrable conformal geometry. It's Einstein-Weyl geometry. So it's actually natural to assume that this conformal structure will be Einstein-Weyl on every solution. This is indeed the case, and the vector omega can be calculated. Let me now show you our results in this direction. Right? So what can we say about a generic Hirota equation? So now we look at a general Hirota equation, and we require that its conformal structure is Einstein-Weyl on every solution. I will call such equations PDEs with Einstein-Weyl property. Yeah, PDEs with Einstein-Weyl property. You see, characteristic conformal structure, it makes sense for any second order PDE, not necessarily Hirota type. Just any second order PDE has a characteristic conformal structure. Right? So this question makes sense for any PDE. But let's first see how it works for Hirota type equations, because here the results are quite complete. First statement, you see, when I say that this equation has Einstein-Weyl characteristic conformal structure. Okay, we don't have a full picture here. We only have conformal structure is a metric. It's part of the Einstein-Weyl geometry. But where is the k-vector, right? It turns out, so k-vector is a somewhat more mysterious object. But it turns out it can be reconstructed using Einstein-Weyl equations, and it can be reconstructed uniquely, right? In particular, for Hirota type equations, there is no freedom for this k-vector. It's just given by this formula, always, for all Hirota type equations. So you see, it depends on the equation. It depends on the equation uniquely, right? It's just given by this explicit formula. If you know the conformal structure G, you know its inverse, right? You just apply this formula here. D is a total derivative. Total derivative. Why do we need total derivative? Because G components of the metric, they depend on jets of the function U, right? Therefore, we need total derivatives. Okay, so for omega, we get this formula. It's one and the same for all Hirota type equations. There is no freedom here. It's rigid. Right. Then we proved, it's proved with Boris in this paper, right? With Boris Kruglikov in this paper. We proved, first of all, we established this formula, right? It works for all Hirota type equations, and in fact, for many other equations. But it's not universal. In general, it's not correct. You need some extra terms. I will discuss this later. This is a universal formula for, let me say, translationally invariant equations. This is not a very precise statement, but in many cases it's true, but not always, right? For Hirota type equations, it's true. Okay. Then Einstein-Weyl property is equivalent to the existence of a Lux pair in commuting, in lambda-dependent commuting vector fields. This is one thing we proved. And then we proved that the Einstein-Weyl property is equivalent to integrability by hydrodynamic reductions. I don't want to stop on this, right? I discussed this some time ago, and I don't want to stop on this. There is another definition of integrability based on hydrodynamic reductions, and this definition is equivalent to Lux-Payne commuting vector fields, and it is equivalent to the Einstein-Weyl property. So I will not stop on this in detail. Let me now show you some classification results, just some examples of integrable Hirota type equations in 3 dimensions. So we already saw this example of DKP, right? Then there is a in all of these cases, the k-vector is given by the formula on the previous slide. You don't need to guess it, you just compute it explicitly, right? Same as characteristic conformal structure, you just calculate it. You do not need to guess it. Then this Boyer-Finley equation, or two-dimensional dispersionless Toda, 2 + 1 dimensional dispersionless Toda. This is also has Einstein-Weyl structure in every solution. Then its modification, it's called dispersionless Hirota equation. Just 3 exponentials. This is also integrable. Then we have a peculiar, quite a tricky example, which was found by Maxim Pavlov. You see this example as a function of uxx. And if you impose require integrability of this PD, you'll get this Chazy equation for f. F is not arbitrary. It must satisfy this Chazy equation, all right? And we know that this is a well-studied PD, and we know that its generic solution is the so-called Eisenstein series. It's called E2, Eisenstein series. So it's a quasi-modular form, right? So this was the first, to my knowledge, this was the first example of a PD, of a dispersionless PD, where modular forms occurred in coefficients, in the coefficients, right? So looking just at this example, so the requirement of integrability implies that this function is a modular form. So this is quite non-trivial. And this tells us that in general, we shouldn't expect a simple answer to the general classification problem. So what is the generic, the most generic integrable Hirota equation? We shouldn't expect a simple formula. And fortunately, we found eventually a formula. I will just say some words about this, but I'm not going to stop on this in any more detail. All right? We proved some time ago that Hirota type equations, generic integrable Hirota type equations, depend on 21 arbitrary parameters. All right, so the function f defining Hirota equation, it satisfies a certain compatible PD system, and the generic solution.
Простите,
yeah.
21 scalar
Constants. 21
okay.
constants.
Okay.
21 arbitrary constants. Like, for instance, these PDs, in this terminology, this PD, it depends on 3 arbitrary constants, because a solution of a third order ODE has 3 constants, right? You see, this ODE has 3 constants in its general solution. So this ODE depends on 3 constants in my language. Okay? So, but a generic Hirota equation, it depends on 21 arbitrary constants. Because this is a very special example, right? And then we proved with with Fabian Clery, we proved that this generic integrable Hirota equation, which we call Hirota master equation, is expressed in terms of theta constants. Let me not stop on this, because this is not the topic of my talk. Right? So it's a highly transcendental function, right? Generic integrable Hirota equation. But this special function is well understood, it's well known. This is called an even theta constant in genus 3, right? Anyway, I'm not going to stop on this. Now, okay, I'm coming to the main subject of my talk. In fact, I think I have 14 slides, right? I'm on the 8th. I'll probably have to go a bit faster. So now I'm looking at generic second order PDEs, and I'm asking a question. What can we say about those PDEs for which the Einstein-Weyl structure, the characteristic conformal structure, is Einstein-Weyl in every solution? So here is a summary of our results, right? Some of them are proved, some are conjectures, right? First of all, again, a PDE defines you a conformal structure, but not a covector. It doesn't immediately give you a covector, omega, right? It turns out that this covector can be reconstructed uniquely in generic case. So for this omega, we get the following formula, right? The following formula. If you look at the first bit of this formula, it's something which was in our, for Hirota equations. So it's exactly the same formula as that works for Hirota equations. But in general, we need these extra terms, which depend on lower jets, on lower jet variables, right? And unfortunately, our result here is very, how to say, it's very implicit. What we proved is that for generic second order PDEs, these additional terms phi s are uniquely determined by the equation. You do not need to solve any PDEs. You find them from a certain, you find them algebraically by solving a certain linear system. Now, what means generic? What means generic? Generic, for instance, it is sufficient to assume that our PDE is not of Monge-Ampere type, not Monge-Ampere equation. So all examples, by the way, I showed you on the previous slide were not Monge-Ampere. Like DKP, Bohr-Finley, they are not Monge-Ampere equations, right? So if equation is not Monge-Ampere, then this...
let us clarify, what do you mean by Monge-Ampere? Expressed in terms of determinants.
Yeah. So I'll give you a definition. So what is Monge-Ampere? Monge-Ampere equation. So you take a matrix of second order derivatives, Hessian matrix of this function, right? UIJ, 3 by 3 symmetric matrix. Then you take its determinant, all its 2 by 2 minors, all its entries, and the constant term, right? So altogether you have 14 things, right? 14 terms. Determinant, then there are 6 2 by 2 minors, 6 entries of the matrix, and the free term. So you have 14 terms. And you take the arbitrary linear combination, right? And set it equal to 0. And the coefficients of this linear combination are just arbitrary functions of first order jets, right? This is a Monge-Ampere equation. All right?
Yes, I just wanted to make it clear. Yes, thank you.
Yeah, linear combination of minors of the Hessian matrix with the coefficients which are functions of first order jet variables. Okay, so if our PD is not Monge-Ampere, for some reason, for Monge-Ampere equations, it's a little bit more tricky, right? It's more rigid for non-Monge-Ampere equations. If our equation is non-Monge-Ampere and satisfies Einstein-Weyl property, right, then these coefficients phi s can be reconstructed. Unfortunately, we have a program that computes them, but it's not possible to write them in a journal paper. They're just horrible expressions with thousands of terms, right? We do not have a clear formula. I doubt it exists. I don't think it exists because we did everything we could to simplify it, but still we have thousands of terms in each component. Phi 1, phi 2, phi 3. We just have 3 functions. Phi 1, phi 2, phi 3. Each is a horrible expression. But I'll show you examples of computations of these coefficients. However, if you have these coefficients computed in terms of the equation, you can express these phi's uniquely in terms of your equation, right? And its derivatives, right? Then everything becomes efficient integrability test because you know K vector, you know G, you know the metric. You can directly check Einstein-Weyl conditions modulo the equation, right? It's a direct calculation. You don't need to integrate anything. You don't need to solve anything. You just check certain identities, right? Modulo the equation. All right. Then there is a general paper by Boris Kruglikov and David Calderban. They proved that Einstein-Weyl property always implies, in fact, is equivalent to the existence of a dispersionless Lux pair with some genericity assumptions. Not arbitrary Lux pair, but a Lux pair with certain genericity assumptions. And okay, and then we observed the following rigidity. We observed the following rigidity phenomenon, which we formulated as a conjecture. So if you take a generic PD of this form, right, which is not Monge-Ampere, right, and which is Einstein-Weyl on every solution, all right? Whose conformal structure is Einstein-Weyl on every solution. Then all dependence on these first-order jet variables can be eliminated by a contact transformation. So it's just an artifact of a change of variables. In fact, you can eliminate them entirely and reduce your equation to the Hirota form. I'll show you some more precise statements, which we can prove, right? Some examples of this phenomenon, but in general, we can't prove it yet. Okay, then I'll give you some partial classification results. So the first is we looked at equations of this form, all right? The left-hand side is a Monge-Ampere expression in second-order derivatives, and the right-hand side is just some function of first-order jet variables. It's a Monge-Ampere equation, by the way. Right, but f is some unknown function. And the question is, for which functions f will this equation satisfy Einstein-Weyl property? Okay, so first of all, in this case, we compute the covector, the metric. It's this. You see, it depends explicitly on this function f. At this stage, f is arbitrary, right? We get restrictions for f later. So this is our conformal structure. Then we apply our test and we get a covector. And you see this covector omega. Oops, it doesn't want to highlight for some reason. Okay, this covector omega doesn't want to highlight this covector. All right, this long formula, you see, it depends on derivatives of u. It depends on a function r, which where r is this. So r depends on this function f. All right. So the dependence on the function f is in this function r. So, but still, this formula confirms the statement that covector omega is expressed in terms of the equation. You see, we haven't even formulated integrability conditions for this function f, but we expressed omega in terms of f already before we formulate integrability conditions, right? This is what we mean that omega can be explicitly determined. All right. Then we impose, for this g and omega, we impose Einstein-Weyl conditions on every solution, and we get classification results. We get these 6 canonical forms. 6 canonical forms where we have Einstein-Weyl property, modulo certain equivalence transformations, right? So this is one, it's just an illustrative classification result. Okay, let me show you another similar computation. Now we consider quasi-linear wave equations. We consider PDEs of this form. Again, here f is an arbitrary function of its arguments. The question is, for which functions f will it be Einstein-Weyl, this equation, right? This is the conformal structure, and this is the covector omega. Yeah, at this stage, you see, this bit is determined in terms of the function f, but here phi of t is some function which can also be expressed in terms of f, but by a more complicated formula, which I'm not showing here. It's expressed in terms of f by quite a tricky formula, but again, it's an explicit formula. I'm not showing it here. Then we impose Einstein-Weyl conditions for this pair, g and omega, on every solution. And we get these 6 canonical forms, these 3 and these 3, right? By the way, some canonical forms are translationally invariant, but for instance, this one is not. This is not a translationally invariant canonical form, and they are contact non-equivalent, these cases. These are all cases. All right, so you see, you can obtain partial classification results. Unfortunately, the general classification result is quite tricky. All right, do I have another like 5-10 minutes?
Sure, you have, you have half an hour.
No, I think 10 minutes will do.
Okay, it's up to you.
Okay. All right, then dispersionless Lux pairs. Let me show you the result. The result which gives you, suppose you have a PDE. So suppose you have a PDE with Einstein-Weyl property, right? And suppose you found the corresponding G and omega, the corresponding characteristic conformal structure and the covector omega. The rest of this on this slide is entirely algebraic. So I will show you how to write down the Lux pair without any integration. It's just an algebraic procedure. Based on G and omega, you just explicitly write down the Lux pair. The procedure is the following. First of all, you express your metric in terms of forms, forms, in this form. Oops, it doesn't want to highlight this metric G. Theta 0, theta 1, theta 2 are 1 forms. You see, to represent your metric, you see any quadratic form can be reduced, of Lorentzian signature, can be reduced to this form locally. Okay, you have to solve some quadratic equations to find theta 0, theta 1, theta 2, but it's an algebraic procedure. Okay, first you represent your metric in this form. It's called the null coframe. Let V0, V1, V2 be the dual vectors, dual frame. These are covectors, theta 0, theta 1, theta 2 are covectors, 1 forms, and these are dual vectors. Let us introduce structure functions by these commutator expansions. Yeah, by this commutator expansion. This is all we need, in fact. Then the Lux pair is given explicitly by these vector fields, where V0, V1, V2 are this dual frame. Lambda is a spectral parameter, and these coefficients m, there are two coefficients m and n, and these coefficients are given by these explicit formulas. This is m, this is n. In terms of the formulas are complicated, but okay, they're absolutely explicit. You do not need to integrate anything, right? Now, to summarize, in fact, the conclusion here at the very end, written here in red, is a bit, at least to me, it's a bit surprising. Suppose you have a dispersionless integrable PDE, okay, in 3D, second order PDE, then we already know if it satisfies Einstein-Weyl property, then its covector is expressed in terms of the equation uniquely by algebraic procedure. You do not have to integrate anything. Also G, so both these objects, G and omega, are expressed algebraically by the equation. Therefore, from what I just showed you, the Lux pair, this Lux pair is expressed algebraically in terms of the equation. You do not need to integrate anything. It's just an algebraic consequence. This is a bit, this sounds a bit confusing because we are used to to find the Lux pair. Suppose you have a PDE, you know it to be integrable. To find that Lux pair, you need to integrate something. You need to solve some overdetermined system, right? And it's not the case here. Yeah, if you know your PDE, dispersionless PDE is integrable, you just write down the Lux pair by explicit formula. You do not have to guess any coefficients. It's just explicit, unique procedure. This is a bit strange to me, right? It was unexpected, at least. Okay, and then I will show you two rigidity results. Rigidity result 1. So, some time ago, we classified Lagrangians of this form, integrable Lagrangian densities of this form, for which the corresponding Euler-Lagrange equation will be integrable. Yeah, will have Einstein-Weyl property on every solution. So if you take this Lagrangian, highlighted Lagrangian density, write down the Euler-Lagrange equation, it will be a second order PD, quasi-linear second order PD. Right? We ask it to be Einstein-Weyl, right? And then this condition of Einstein-Weyl property imposes this complicated OD for the function phi, right? Phi is a function of ut, is not arbitrary. It has to solve this fourth order ODE. And remarkably, its general solution is again a modular form. It's not a Chazy equation as before, it's another modular form called Eisenstein series. There is a notation for this series. It's a well-known object in the theory of modular forms, right? So again, it's a non-trivial function, this phi of ut. So what we tried to replace this function phi of ut by something more general, by something like this. A function of t, u, and ut, and run the same test, run the integrability test. Actually, when we started this, I was expecting to get something nice. I was expecting to get a non-trivial deformation of the modular form. There are, in fact, in the theory of modular forms, there are such deformations. They're called Jacobi forms. So they depend on two variables, Jacobi forms. Modular forms are functions of one variable, and Jacobi forms are functions of two variables. So I was expecting to get something like this from integrability requirement. But what we got is this. So we applied the test, and we got that f must be this function, right? We found it explicitly, right? Here, h and g, arbitrary functions of u and t, and phi, this function, is a generic solution, is this Eisenstein series, generic solution of this ODE, right? So we found this f explicitly. And then it was observed that, in fact, in this ansatz, these functions g and h can be eliminated. In fact, this is the result of applying contact transformation to the Euler-Lagrange equation of this Lagrange, right? You apply a certain contact transformation, you get this more complicated Lagrangian. So they're equivalent. They're not different. Look different, but in fact, this dependence on t, u, and t can be eliminated. Right, another rigidity result of similar nature. We looked at, so again, I took the equation found by Max Pavlov. Here, this phi of uxx is a Chazy. Phi solves Chazy equation. So again, it's the Eisenstein series. And what we did, right, we tried to deform it. We tried to look at PDEs of this form, of the form 4, where this function f now depends on all variables, x, u, ux, and uxx, right? Again, at the beginning, I thought we will get something interesting, right? But unfortunately, we got the same answer. We got that f, if you apply Einstein-Weyl test, you'll get that f is explicitly given by this formula, right? Here, g and h are again two arbitrary functions which satisfy a certain constraint. By the way, f doesn't depend on u. You get it as an integrability condition. So this u element cannot enter, right? You get this ansatz. And again, you can easily show that everything can be eliminated. So it's not a new equation. It's obtained from this equation by contact transformation, right? And we looked at some other examples, and it's clear that you see if a generic second order PDE has Einstein-Weyl property, then all dependence on first order jet variables can be eliminated, right? This was another, I would say, surprise. I wasn't expecting this result, right? But this was another surprise. But on the other hand, you know, there are many papers where people take, say, KdV equation, Korteweg-de Vries. They put, instead of constant coefficients, they put coefficients depending on t or xt. Just KdV with coefficients depending on x and t. They apply one of the integrability tests, and they get certain expressions for these coefficients, which imply that they can be eliminated by change of variables. So they're unessential. They're fake. This dependence on x and t is fake. It can be eliminated. So exactly the same thing happens here, right? All dependence on first order jets is fake, right? And in fact, this is my last slide. I will just say a few words about possible generalizations, or maybe just three remarks. Remark one. So we looked at equations whose conformal structure is Einstein-Weyl on every solution. Okay, but let us impose a simpler condition. Let's impose the condition that conformal structure is just conformally flat on every solution. It's a stronger constraint, all right? What can we say about PDEs whose conformal structure is flat on every solution, all right? We conjecture, we have no proof of this, and the proof should be, and a proof should not be easy, right? But it's quite clear that any such PDE can be reduced to this form. In fact, it's a Laplace operator, constant coefficient operator, second order constant coefficient operator, Laplace and a constant coefficient metric applied to U equals some function depending on lower order jets, on first order jets. So it's just, you see, all dependence on all nonlinearity from the symbol can be removed by contact transformation, right? So it's clear that if you take a PDE of this form, it's clear that its symbol is just constant, right? Because F doesn't affect the symbol, right? The symbol is determined by this constant coefficient operator. It's constant on every solution, so it's flat on every solution, right? For equation of this type, it's easy. It's obvious. The converse is also true. If conformal structure is flat on every solution, then your PDE can be brought to this form by contact transformation. This is a conjecture at this stage. Then remark two. We have proved, okay, that covector omega can be reconstructed in terms of the equation, for equation which satisfies Einstein-Weyl property. If the equation is sufficiently generic, in particular, if it is not Monge-Ampere, for instance. If the equation is not Monge-Ampere, then covector can be reconstructed. But in fact, we believe that a stronger result is true. This Monge-Ampere restriction is also not so important, right? What is important is that the characteristic conformal structure is not flat on generic solution. So in other words, our PDE is not of this form, right? If our PDE is not, if characteristic structure is not flat on generic solution, it's already enough. You can already reconstruct omega explicitly in terms of the equation. Okay, examples show that this is true. And finally, the last comment is the following. We looked at various classes of PDEs in 3D, which are integrable by the method of hydrodynamic reductions, right? We looked at several classes of such PDEs, and we proved that all such PDEs, they must satisfy Einstein-Weyl property. Conformal structure must be Einstein-Weyl in every solution, right? However, the method of hydrodynamic reductions is not invariant, for instance, is not contact invariant. It requires a certain form of the equation for you to be able to apply the method, right? It is sensitive to the form in which your equation is written. However, Einstein-Weyl property is not sensitive to this form, right? It doesn't matter, it's contact invariant. You can make a change of variables and Einstein-Weyl property will be preserved. So we can say, okay, let's say that our PDE is integrable if it satisfies Einstein-Weyl property on every solution. Then this is contact invariant. However, what can we do with such PDEs? We can't solve them because these hydrodynamic reductions are no longer available. Okay, hydrodynamic reductions are also quite implicit things, but still it's something, at least it's something, right? But if we lose this, we have nothing. We just have Einstein-Weyl property and no solutions at all, even implicit, very implicit, right? However, we have this conjecture that Einstein-Weyl property implies that you can eliminate all derivatives, all dependence on low-order jet variables. So in fact, your PDE is contact equivalent to to Hirota type equation. And to such equations, Einstein-Weyl property, the method of hydrodynamic reductions is already applicable. So in other words, to summarize, you can use Einstein-Weyl property as a contact invariant approach to dispersionless integrability, because if it is satisfied, you can eliminate all low-order jets. Everything is reduced to Hirota form, right? So I think I would stop here. Thank you very much.
Zhenya, thanks a lot. Questions, remarks, comments? Boy, don't you want to add something?
I think it's fine, thank you.
Boris?
Yes, hi.
No, Boris knows everything.
Yes, I understand, but maybe he know more.
Okay.
Well, Jenny promised to show some scaling formulas, but
Yeah. I want to.
Scaling.
Yes. You said that formulas, explicit formulas, are horrible. Not for.
No. I said I will not show.
But maybe we can have a look at the screen.
Okay.
Yeah.
What I meant is this. Sorry, I'll show you what I meant. I meant something like this. Sorry, something like this. This formula for omega, right?
that's not scary.
This is not so scary, right? Still, it's complicated. You see, it depends. This coefficient R, it depends on F. But you see, if you take a generic PDE, the formula grows exponentially. Yeah, this omega becomes a very complicated object. And still, I doubt there is a good formula for it, to be honest.
I mean, maybe I add one thing. So
Yeah.
actually, this class of equation is equivalent to a deformation of Lionia-Bogdanov equation. And formula change, actually. So some of them become simpler, some other becomes actually more complicated. So yes, there's also explicit formula for those deformations, but yeah, so this doesn't help. So that's kind of point transformation, and something simplifies like Lux pair, but some other things get more complicated, like Einstein-Weyl structure.
Okay.
Okay, Boris, thanks. More questions, more remarks. Okay, Jane, thanks a lot. I want to add that you are always welcome at our seminar.
Thank you, Yosef. I'm always trying to attend when I can.
Yeah. Okay, so we meet next Wednesday, and we shall have talk by Gosha Sharygin. Everyone is welcome, and I wish you a good week and to be healthy, and see you next Wednesday. Bye-bye.
Thank you very much. Thank you.
Bye-bye.
Bye.
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 Okay.